not only enjoy all the talks, but also we connect to each other. We encourage your show up. Participation actually is an encouragement to all of us, including myself. As I mentioned before, never feel so closely connected to so many professionals across the globe, all the way from all 6 continents, actually. It is certainly a blessing. ARMA hydraulic fracturing Robe talks is a Cairo technical talk with the purpose of connecting, stimulating, and entertaining professionals during this pandemic, with everybody practicing social distance at home. Over the past, since April 6th, we had such a great speakers and participants. This series will continue. Some of you may have heard we are trying to migrate this series into ARMA website as people returning to office. This is an ongoing process, and please bear with us with patience. Before we do that, we will continue this series in current format. When the time comes, I will announce the next through the HFC newsletter. So if you have not received my newsletter, please send me an email. I'll get you on the email list. So today, and also because it's Cairo Technical Talk, we don't require presenters to release any, but we'll pass on if anything the presenters have been kindly releasing, including today. Egor has kindly, he will go through the internal approval before finally releasing, but we will record this and see how it goes. From professional point of view, we ask you not taking any pictures or recording by yourself. We all appreciate the hard work and efforts by presenters. So today, Professor, I still call you Professor, Egor, Dr. Egor Dontsov. I'm going to talk about one significant aspect of hydraulic fracturing. As a matter of fact, many of us facing the similar problem, similar challenges. We are headache of this. Is when you're dealing with rock heterogeneity, especially laminations, like the picture showing in the background, what we're going to do for model inputs. So today, Egor will talk about how to deal with that with the title Homogenization of high resolution rock properties for hydraulic fracturing model. Egor, I know Egor for a while. Besides handsome, Egor actually is a very sharp mathematician, and he studied with Professor, one of the famous mathematician professor at the UBC, University of British Columbia, and Professor Anthony Pierce, who will give a talk next Wednesday. And Egor actually was assistant professor at the University of Houston before he decided to have a taste of industry flavor. And I was joking actually, even though right now we're on the dark side of the industry cycle, but everyone worked in this arena for long, especially Sid Green, for example, knows way better than anybody else. When you're in the bottom, you know the industry is climbing up. When you at the top, you better be careful because you know the bottom will come. So this is the nature of this industry. So we wish everybody safe, healthy, and stay connected. So Egor right now, he's, as I mentioned, he's developing numerical code for ultra fast hydraulic fracture and reservoir modeling, target especially patch steel developments. If you look up especially ERTEC and ARMA, you will find some of his recent publications with his colleagues. Fantastic work. So with that, Egor, feel free to take over. Again, if you have any question, please type in the chat window. Egor will answer them after his talk. Talk will be 45 minutes, a QA included. And we normally extend this Zoom meeting even after speaker talk. So feel free to stay longer. And I'm sure if within the time window, Egor couldn't address all the questions, he will follow up through emails. And last but not least, we want to thank everyone, especially speakers. The next, especially the month of June, we have a very good lineup. As I mentioned, Professor Anthony Pierce from UBC, and also we have Forge, John McLennan, talking about Forge. We have GTI colleagues talking about hydraulic fracturing test site, Scott Reeves and Jordan. Then we have Alex from Shell, share his insights as well. So stay tuned. We have more to come. So Egor, feel free to take over. Thanks.
All right. So thanks again for the introduction, and I'd like to thank you again for organizing this talk series, and thanks for letting me speak at one of the today. So as you can see on my slide, right, I'm going to talk about the homogenization of high resolution rock properties, right, and with emphasis of hydraulic fracture modeling. And in the background of the slide, you can see a photo of the core, right? So just to it's important to understand what are we fracturing, right? And so this is again the picture of the core and the characteristic size, in the vertical dimensions about 3 feet or 1 meter, and you can see the layering, right? Layering is thin. I mean, even visually you can see very contrasting rock properties. You can see different structure and so on. And so the main question is, what do you do about it? I mean, do you just ignore it and then average everything out, or you somehow introduce this into the model, right? So that's the main question that we are trying to answer here. But before, let's give a little bit of overview of where we are from the hydraulic fracturing development, right? So overall, the current trend is to do this massive developments of pad scales consisting of multiple wells, and maybe landed in different formations, different benches, and some of them are fractured like long time ago and been on production for several years. So these are parent wells. Some of them are child wells, and for every well, as you can see here, you can see we have multiple stages, 30, 40, 50 stages. And each stage has several clusters, could be 4, 5, 10, 15 clusters. And so overall, if you just count the number of fractures, I mean, think about it, from each cluster, you have single hydraulic fracture. So within the stage, you have an order of 10 fractures, and then you have an order of 10 stages, maybe 30 stages. So you're talking about several hundred fractures per well. And now you multiply it by the number of wells. Now you're talking about thousands of fractures, right? The question is, do we want to model it, first of all? And then if we do, then how do we model it? So an order of thousands of fractures. On top of this, and I just show you the piece of the core, right? Photo of the core, right? And its size was approximately 1 meter, and you see all this layering, and the sizes or dimensions, in in the vertical scale, right, between the wells in order of hundreds to thousands of feet, right, or several hundred meters. And so the question is, on top of having that many fractures in the system, we also have high resolution rock properties, and the question is again, how do we reconcile all together? How can we model this path scale development given the high resolution rock properties? Okay. And so here, let me give you just a brief overview of something we've been working on here in the lab since early 2017, maybe late 2016. So these are just approximate dates, but I just want to give you a big picture or bird's eye view of how we're addressing such large scale problems. So again, early 2017, we were working on homogenization. Again, this is the primary purpose of this talk, but this is again just to understand it's one of the building blocks of the whole model, if you want to. Okay, and then later in 2017, we also work on the concept called equivalent fracturing. So again, if you go to homogenization, the purpose is of rock properties, right? The purpose is to upscale the rock properties, all of them, toughness, Young's modulus, stress, all of them, leak off to lower resolution so that you can run numerical models, right? So you cannot run numerical models on millimeter or centimeter scale resolution. So you need to upscale it to 10 meters or in feet, 15, 20, 30 feet, and then do the modeling. Then as I said, in path scale developments, we're dealing with thousands of fractures. The question is, do we really need to model each individual fracture? And the answer is maybe not necessarily. And to upscale the number of fractures or reduce the number of fractures, so we've been working on the concept of equivalent fracturing. And the thing is again, on the picture on the left, you can see simulation of one station, homogeneous rock, no layers, no propant. But even that, because you have limited entry, for some conditions, if you have low viscosity fluids due to stress shadow, you have very strong interaction between the fractures, and so they develop these complex shapes, right? But the thing is, we don't need to model each individual fracture. We can represent all this by a single equivalent fracture, okay? And as you can see in the pictures below, one of the main characteristics for path development is stress shadow. And here we plot the stress field from this complex set of fractures and a single equivalent fracture. Of course, it is wider, right? Because essentially you add up contribution from all of the fractures. It is wider, but has same dimensions and same, surface area and volume. And the induced stress field, the far field stress, are identical pretty much, right? I mean, you do lose some complexity, right? Near the wellbore, but far away identical. So that's the main concept, right? So instead of modeling, say, 10 fractures, you model with 1. And now for the path scale, again, instead of modeling 1,000, you go with 100, right? Or hundreds. And now it becomes much easier and numerically faster to model. Then something again I presented last year at URTech, we worked on ultra-fast hydraulic fracture model. And again, you need to think about in terms of all the previous steps. So we use homogenized rock properties together with equivalent fracturing. And now we want to model this, resultant equivalent fracture quickly. And again, you can think about upscaling the numerical simulator. You can take the fully three-dimensional simulator and try to represent it by a simpler simulator with just say fewer degrees of freedom and assuming, like in our case, elliptical fracture shape. And now you can run it, 100 or 1,000 times faster, right? So, and again, in terms of stress shadow, I mean, you cannot see the difference here on the left. We have fully three-dimensional simulation of induced stress from several stages, several fractures. Fractures are a little bit non-planar, I don't know if you can see here, and the ultra-fast. And just to give in perspective, so to get the picture on the left, I mean, you spend days on running the code just to get this. And the one on the right, again, you can see similar fracture geometry, similar stress field. It's less than a minute, okay? So that's kind of the way of how to consistently upscaling one thing after another, be able or develop an ability to model the path scale development. And finally, we all, even though we all, care about the fracturing, right? So we're in the fracturing community. We shouldn't forget about depletion, right? So as I said, some of the wells are depleted on the pad or can be depleted. For instance, you may have, I'm just talking about, say, this picture with fractures. You can have lower, several 3 wells here are depleted, and then you fracture upper wells within the presence of the depleted zone, okay? And so the question is, how do we model this? And so what we have developed is, again, the fast model, or think about upscaling of the reservoir model, okay? And something we are, hopefully will present at URTech, one way or another, if, this year, if it's going to happen or not. But the idea is, again, I mean, you do introduce some approximations, but you try to keep the first order of magnitude important effects and try to run, the reservoir model on the whole system of wells quickly, okay? And as just an example, here we did, again, it's coming in the URTech paper, some matching of the production data, and we varied 2 parameters, and we run the model 400 times, fracturing and reservoir model to try to match the production rates for all the wells simultaneously. And here we show the error, and you see that the error is actually non-unique. There's no unique solution as expected, actually. And so we can either have different permeabilities, or what we did here is try to change the surface area. The motivation is that many people say that, well, we waste a lot of resources when we fractures, and that only, say 20% of fractures contribute to 80% of production and so on. And so we decided to model this and see how does it work, okay? And here's a picture of on the bottom, again, just to finish up the, the overview, is you have, several wells here. The first 6 wells we were fractured and produced, and here we plot the stress, the in situ, minimum in situ stress. We have lower stress right where we have production, high stress near the fracture tips. And so you see how fractures kind of, some fractures grow into the depleted zone, and some fractures grow around it because of this little bump in stress. But anyway, just an overview of how can it all be combined together all the way from the rock properties to the depletion modeling. There are approximations in every step, and we try to have a rigorous validation for every of the steps, okay? And again, this was a big picture, and I hope it convinced you that homogenization is one of the first and critical steps in doing all this, because every numerical model has certain resolution, and we do need to have a way of coarsening it up, but such that we don't lose too much, okay? And so here on the bottom, I specify the high resolution properties, typical properties that we use in a hydraulic fracture model: the horizontal toughness, the vertical toughness, Young's modulus Poisson ratio, leak-off coefficient, and stress. Okay, and now let's try to see how can we upscale all of them, right? So we don't focus on one. We need to check how do we upscale each one of them. Okay. And again, depending on what data you use core measurements or log measurements, you may have slightly different resolutions, but that's the effect of resolution is actually another story. So far, let's think that we have several inch resolution, and we do have this high small scale oscillations, again as supported by the picture of the core, right? We cannot have the same properties if we have very, very different rocks adjacent to each other. Okay, so let's start. But first, let me outline the previous studies, right? So actually, I started working on homogenization some time ago, and before joining the lab, it was in 2016. And at that time, what I was doing is I realized that we can homogenize stress and make it use the average stress. And actually the focus was only the stress, okay? So everything else was constant. And we can homogenize stress away from the fracture tips, but near the fracture tip, we cannot do this. So there's a small scale layering of small scale variation of material properties near the tip are important, okay? So far away, we kind of can smooth everything out, but near the tip, they're important. And you also probably heard the talk by people from Lawrence Livermore lab, right? They did numerical simulations, right, in formations with periodic variation of stress. Okay, so as shown here, so it's planar fracture. We have high stress, lower stress, high stress, lower stress, and they realized that because of this layering, The fractures have a height containment, and we can capture this by means of adjusting the vertical toughness by certain value as shown here, right? So basically, we have delta stress in the layering times the layer size, square root of layer size. Okay. So, and as you will see through the talk, I mean, we'll get to similar results as well. But again, we not focus just on the stress, but on all other parameters as well. But it's good to outline what is known so far. So let's start, right? So one property at a time. So we do the elastic properties. Okay, this is a little bit more mathematical. But back in 1962, Backus introduced the averaging for anisotropic layered material for the purpose of wave propagation, right, in geophysics. So the idea is the following. So say you take a cube, layer K cube, okay, and you assume that every layer is elastic, transversely isotropic, and you apply the average strains in horizontal directions, right, and average stresses in the vertical directions, and then just solve the elasticity equations for every layer, okay, and then come up with the average elastic response of such layered block. Okay, there's some mass involved, but it looks worse than it is. But overall, you can get the Cij. This is just to get a notation, right? So we have a quantity, any quantity we're going to talking about, say leak of toughness or stress. We have a layer quantity. So in the brackets, we're going to talk about the average quantity, and average means like this weighted average, right? So you may have different thickness of the layers, right? You may have thicker layer, so Hi is thickness of each layer, and Qi is the quantity. So some layers are thicker, some layers are thinner. So we introduce this average. And the homogenized, it's going to be Q bar, right, for any quantity. So homogeneous is not necessarily equal to the average. For some quantities it is, but not for all of them. Okay. But anyway, based on Backus averaging, we can actually deduce allCijs for transverse isotropic material, the homogenized, based on averaging of all these coefficients. Okay. And again, you may refer and look through this publication to get to the details. But let's see what are the implications. Okay, I mean, first of all, even if you have elastically isotropic layers, after you homogenize, you get transversely isotropic material, right? So the question is, what do you do about transverse isotropy? And right, I mean, you've seen a talk by Breeze earlier about the effect of anisotropy, but one way to quantify it is to introduce the apparent elastic moduli for the fracture propagating in the horizontal and vertical directions. Okay, so you can propagate, perpendicular to layers and along the layers, and these are effective compliances or stiffnesses of fractures are slightly different. Okay, and so if you have just say contrasting Young's modulus, then after homogenization, then now you have transversely isotropic material. So the question is, what do you do about it? Okay. And we actually solved or addressed this problem to some extent with my graduate student back in 2018. So what we said that what if we have the periodic material and you just change your Young's modulus from hard to soft, and then you homogeneous using Backus averaging, you have transversely isotropic material. And the question is, how does the fracture aspect ratio changes as a function of anisotropy, okay, or the ratio between these two moduli. So again, for the purpose of this presentation here, we want to see the contrast between the homogenization and averaging, right? If you just have periodic variation of Young's modulus and we take the average, right? So we're going to have isotropic material. And now if you compute this apparent moduli for the fracture going vertically and horizontally and see what's the difference, magnitude of the difference between this apparent moduli and the average modulus, okay? So the average, so if it's 1, then you can do average all elastic properties and then you shouldn't worry about it, okay? And then the x-axis is the ratio of the contrast of stiffness of Young's modulus, okay? So let's say if you have stiffness contrast for about 2, now you're off in about 5%, okay? So the average versus homogenization. If you contrast about 3, again, depending on direction, you're off by about 10%, okay? But overall, I think it's relatively small. So overall, this demonstrates the order of magnitude of the effect. So you do change the modulus, but if you change by 5%, it's probably not a big deal, right? I mean, unless you have really strongly contrasting elastic properties. Okay, but at least we're able to understand this. Now, one of the most important things is fracture toughness. What do we do with fracture toughness, okay, and why? So here, let's think, conceptually think about the problem of this hydraulic fracture, and it propagates along the layers, okay, and it has this, we can have this weird shape because of layers, or across the layers, right? So it propagates vertically. And if you're propagating along the layers, it's the, we essentially feel, or hydraulic fracture feels the average, it feels the properties of every of the layer, okay? So that's why it's natural to assume that the average properties, is something that we need to worry about it. But if the fracture grows across the layers and vertically, then it's the property or toughness of this local layer near the fracture tube. That's the one that determines the response, right? So think about if you have one bad guy, one really strong layer with really high fracture toughness, then the fracture is going to be arrested. So you cannot just average out the fracture toughness, because you're not going to account for this really the bad guy, the very bad and arresting layer. Okay. And in addition to that, let's try to think in terms of fracture energies, right? Not just fracture toughness, right? Because it's the fracture energy, from an energetic point of view, that's the one which is relevant for fracture propagation. And so the fracture energy is toughness squared over the apparent modulus, or elastic modulus. And here we introduce the fracture energies in horizontal and vertical directions, okay? Because we, even though if we start with the model with the same horizontal and vertical toughness, as you will see after homogenization, they're different. And so therefore we in general introduce two fracture energies. And for the horizontal toughness, we say when we homogenize, let's preserve the average fracture energy in horizontal direction, okay? As I said, we feel all the layers, and so we take the average. So therefore, when we homogenize toughness, we take the energy of every layer, okay? And then we average it, and then multiply by the homogenized modulus and take square root, okay? For the vertical toughness, as I said, it's the worst layer which determines the propagation. So we really want to preserve the effect of this worst layer. So therefore, we take the maximum, okay? So take the fracture energy in vertical direction, take the maximum, okay? And then multiply by the modulus, take the square root. And you'll see they're very, very different results, right? I mean, first of all, this fracture energy involved, not just fracture toughness. And second is the maximum versus average. In particular, because we're talking about the fracture energies, we will see that even the contrast of elastic properties, a Young's modulus, is going to introduce an apparent vertical toughness, okay, and horizontal as well. So let's just do several examples, okay. We consider a case, a planar fracture with periodically varying Young's modulus, okay. So here are the input parameters: toughness, modulus, stress, viscosity, and so on. And here we want to think about the effect of fracture toughness, right? So we better be close to toughness dominated regime. And here on the right, I show the parametric diagram for radial fracture. I mean, no layers, but still radial fracture. Here we have two-dimensional parameters that determine the fracture regime. So M is storage viscosity, and K is storage toughness. And the M tilde is the leak of viscosity, and K tilde is leak of toughness. So basically, if you have no leak off, you are between M and K. You have high leak off, you're between M tilde, K tilde. If you want your viscosity dominant solution, you want to be near M. If you want toughness to determine the solution or influence the solution, you are near K. Okay, and so that's where we are. Again, we want to focus on the effect of toughness if we want to be near K, because if we now use an example with, say, high viscosity across linked gel, we're going to be somewhere here near M, and we just won't be able to see any of the effects. So as I said, we have the periodically varying Young's modulus, so from 15 to 20 GPa. And when we do all the math, as I just showed, based on Backus averaging, we come up with the average Young's modulus. And as you can see, again, the difference, if you take the average, it's just going to be 20. If you do all this fancy math, it's still going to be very close to 20. So, I mean, it is what it is. But for toughness, it's a big deal, right? So you think you use 3 MPa, but after homogenization, the horizontal becomes 309 and the vertical becomes 3.4, okay? And so we did a numerical simulation using Frac Optima, again, for planar fracture. On the left, you see a solution for layered material, again, with varying Young's modulus. On the right, you have homogenized with these values of toughness, okay? So everything is, there are no layers anymore, so it's just homogeneous material, but they have different fracture toughness. And you see they match very well, again, on average. And just to further confirm this, we plot here fracture size versus time. So here the dashed line shows the fracture length. So the black is for the layered case, the red is for homogenized, and the solid lines show the fracture height. And the gray line shows the solution for the radial fracture, because if you have no layers, then the solution will be, or just simple averaging, the solution will be radial, okay? And so you see how much off we are in fracture height and length. And also because we have layers, right? So fracture doesn't grow uniformly in height or length, right? It grows kind of in steps, right? But when you homogenize, you average all the steps, but you still preserve the overall trend, okay? Second example, periodic horizontal toughness. Okay, still the same base case in your toughness dominated regime. Now let's vary horizontal toughness from layer to layer from 2 to 4 MPa per root meter. And again, once you homogenize, everything else becomes the same, but the homogeneous toughness becomes a little bit more than 3. It's just because of, again, we use the energy, and here we have toughness squared, right? It's not linear function of fracture toughness. And sure enough, if you have the layer, because you have higher horizontal toughness, now you have these X-shaped fractures. If you have a layered material, and once you homogenize, of course, you capture this X-shape. I mean, this is not a very strong effect for horizontal toughness, not as much as for the Young's models for vertical toughness, but still, conceptually, you can see they match very well. The length doesn't match, that precisely, just because we have this little, those fingers, right, for the layered material. But the height matches nearly identical, right? You can see the solid lines, they match identical. Okay. Again, this is just to confirm that, this averaging of the energy, again, this is the energy that is important, fracture energy. That's, again, this is basically provides a validation for this. And vertical toughness, this is the most interesting one. Again, we use 2.5 to 3.5 contrast in vertical toughness properties. Again, because we use the maximum, after homogenization, we use 3.5, right? So we use the maximum. And here again, this comparison for the left is fracture, planar fracture for the layered case. On the right is for the homogenized. And here we have fracture size versus time. And again, you see the same trend that first of all, fracture is strongly non-radial, because again, this gray line corresponds to the radial fracture. And we match the trend, even though we do have this staircase kind of behavior for the fracture height and length, but we do match the overall trend of the fracture growth. Now the stress, right? So we figure out the effect of elastic layers, horizontal toughness, vertical toughness. Now the stress, right? So first of all, we want to preserve the total force acting on the element. And I mean, think about if you're in the middle of the fracture, as I showed you before, the total in situ stress, force caused by the in situ stress on this element should be preserved. So that's why stress has to be averaged, okay? So therefore, if this is gray line shows you high resolution stress, when the average, you just basically need to, do a weighted average and follow this line. But the question is, what do we do? What is the contribution of this difference between this high resolution stress and low resolution stress? And it has to do something with fracture tip, as I showed you before. And so what we do is to compute, there is a formula for computing the delta stress intensity factors caused by, for semi-infinite fracture, okay, which is, again, the model for fracture tip, for semi-infinite fracture. And so we can compute this change of stress intensity factor due to any loading, okay, so it's done a long time ago. And in this case, the loading, or the extra loading that we're not accounting for, is the delta stress, this difference between the average stress or homogeneous stress and high resolution stress. Okay, and then we can transform this change of stress intensity factor with minus sign to change of an apparent additional vertical toughness. Okay, and so, and again, we have everything here. So we know high resolution stress, we have average stress, which is square root of S is distance from the fracture tip. Okay, and so we can compute it. Okay, and I'm going to show you an example how we do it, but let me just outline what are the implications of using this formula is. First of all, we assume elastically homogeneous formation. So it's an assumption, and again, we have to live with this. The integration is to infinity, but we need to truncate it, and we can truncate it because the integral kernel decays as 1 over square root of S being again distance from the tip. So think about we're integrating from the fracture tip towards inside of the fracture. And so we can truncate it over, say 2 or 3 elements. And then once we compute this delta toughness vertical, then we can use the maximum energy principle, right, to homogenize toughness. Okay, so essentially this gives a correction to toughness due to stress on high resolution, and then we apply the concept of toughness homogenization to get it to low resolution. And in general, these corrections for the tip growing upwards and downwards are different. Okay. Because the layering is different, the way you cross the layer from low stress to high stress or from high stress to low stress, it matters. So these corrections are different. So as a result, the homogeneous toughness in the vertical direction or for the fracture growing above the wellbore is different from the one that grows below the wellbore, because the direction matters. Okay, I mean, as shown here, right? So for all the modeling, what we will do is to, in general, assign the vertical toughness in the upper direction above the wellbore, and the vertical toughness to the lower, for the downward direction below the wellbore. Let's again, we showed a lot of examples for periodic properties. So now periodic stress is not an exception. So let's do a periodic stress example. So all this finally looking mass is nothing else but it mathematical way of representing periodic stress. So variation of stress versus depth. So delta sigma being the magnitude and h being the layer size. And what we just do is to plug it in and compute correction for the delta, so for the change of the apparent vertical toughness in a direction going upwards and downwards. Okay, just mathematically can compute these integrals. And again, they're different. Okay, they're different. So let's just try to plot this. So this function f is here, shows the essentially stress profile. It's normalized, but so it have higher stress. The blue shows high stress here, lower stress, and this is periodic, so it's just one periodic cell. The black line shows the apparent toughness correction for the fracture growing upwards or in the positive z direction. So it's here, and the red line shows the change of the apparent toughness for the fracture growing in the negative z direction. And there are different lines because remember I mentioned that the integral here goes from 0 to infinity, but we have to truncate it somewhere. And so we truncated, so here truncated with over one element of one cell, 2 cells and 3 cells, just to see we have convergence. And here it shows the difference of, again, this or convergence versus number of cells. It's not very quick convergence, but the still results converge fairly quickly if you use several number of cells. Let's just go into a little bit more in the details just to understand what is going on. Again, here I show the stress, periodic stress, the blue line. And so this is a fracture, or schematic for fracture growing in the positive z direction. And so the black line shows the change of apparent toughness. Okay, and you can see that the maximum value occurs when the fracture is about to cross, this large stress zone. Okay, so when fracture grows to the low stress zone, the apparent toughness contribution is small, right? So it makes sense because once we average it out, then it's easier for fracture to propagate through low stress zone. But when it goes through the high stress zone, then apparent toughness grows, and then it reaches the maximum right when we're about to cross into the low stress zone again. If you go downwards, then situation is very similar, but it's mirrored, right? Because now the maximum occurs at this point. Okay, so because that's when the fracture is about to cross the stress barrier. And so that's why you can see how these corrections for the upward and downward growth are different, right? That's why we need to introduce the toughness in a direction essentially above the wellbore and below the wellbore, in different manner. But for the periodic case, when you homogenize, the maximum is still the same, right? But in general, if you use field data, they are not the same. Okay, so and I hope this gives you enough motivation to agree on this. And again, for periodic case, we can analytically compute using this equation that the change of the vertical toughness is about in 107 times the magnitude of stress or delta stress, okay, from layer to layer, and the square root of the layer size. And again, this is consistent with previously obtained results from a group from Lawrence Livermore. They just didn't get this factor 107, but it's very close. And then examples, right? So again, with periodic stress, again, we need a toughness dominated regime. Here's our layer size. Here's our delta sigma, 0.1 MPa. And here layer size is 20, it's meters, and the element size is 2 meters. So we have about 10 elements per layer, just make sure that we have a good accuracy. And if you do again all the mass, you can compute the delta change, right, in vertical toughness, about half megapascal square meter. And again, as before, we have layered and homogenized. Again, if you use this value of toughness and add it to 3, right, so we capture the aspect ratio and evolution of height and length accurately. And of course, we can do different contrast, same layer, different contrast. Now we have more effective toughness, and you have, say, to change layer size, you go from 20 to 10 meters. Again, because this is layer size dependent, now we have less toughness, and again, we capture behavior very well. And one remark here is that if you remember, for the fracture toughness and modulus, the results are not length scale dependent, right? So it doesn't matter how thin your layers are. I mean, as soon as your linear elastic fracture mechanics works. But with regard to stress, this is length scale dependent. So if you have the same magnitude of stress oscillation, but larger layers, then you have more effective fracture toughness, right? If you have smaller layers, you have very thin layers with the same amplitude, now you're going to have less fracture toughness, as shown here, right? So this, a very, very important observation. Finally, the last is leak-off, right? So again, your hydraulic fracture simulator depends on elastic properties, toughness, stress, and leak-off, right? This is the last part. So what do we do? Well, first of all, so we need to test the cases here which are close to the leak-off dominated regime, because otherwise we won't be able to see any effect. And so that's why we selected these properties with high value of leak-off. And so far, just to present the total fluid loss through the surface area, we just need to take the average value. And here again, we compare the periodic variation of leak-off, and here we took the extreme value. So we had layer with no leak-off here, and then high leak-off here, no leak-off, high leak-off. So this is extreme variation, and we use fracture efficiencies of about 10 to 20%. So again, it's high leak-off cases. And you can see that after homogenization, if you use layers or you just use the average, you are pretty much, fracture remains radial. You do have this, little bit of elongation because of these fingers, but it's an extreme case, and the difference is relatively minor. And so our conclusion is that it's okay to use average for leak-off, right? Then field data, right? So the thing is, just summarize, what do we learn? Again, so we tried to consistently evaluate the effect of high resolution properties on every parameter that enters the hydraulic fracture model. And for Young's modulus and Poisson ratio of elastic properties, we do use backwards averaging, but overall the effect is not as large, right? So even if you use just averaging, you will be off, but maybe 10%. It depends on the quantities that you're using. It's okay to use average for leak-off and stress, right? But the biggest difference is fracture toughness. Again, both horizontal and vertical. Horizontal toughness, because we average energy, right? Again, we don't simply follow the high resolution data. Actually, what I didn't say is that high resolution is gray and low resolution is black right after homogenization. So we're not precisely following the curve here. And for the vertical, it's a big change, right? So it depends on what stress model you use. It depends on many factors, but in general, the vertical toughness increases relative to the base value, but on the order of 100%, okay? Or maybe more, it depends on the resolution and everything, right? So that's the biggest implication. And here, another thing that we did is we tried to use it just as a step towards validation, see what's actually the implication of fracture geometry. We used ultra-fast hydraulic fracture model, which I mentioned at the very beginning of the talk. And we ran a single stage for some field data, field schedule, field properties, run a single stage at different landing depths, okay? So here we have different depth values from about 5,000 to 9,500 feet. And with a step of 15 feet, we run a single fracture. So basically, say you have 5,000, you run a fracture, 5,015, you run the fracture, 5,030, and so on. So every 15 foot, you simulate the fracture. And what we show here is fracture height. So color shows fracture height in feet, and you can visually see the fracture height as a function of your landing depth position. So this allows us to see, you have here hundreds of simulations. You can see how how these, you know, basically you see a lot of fractures at the same time for different properties. Okay, and you can see whether homogenization preserves the geometry or not. And so here, because it's ultra fast, we run it at a very high resolution, 5 centimeter to inch resolution. It was very slow, but still manageable. And then we did homogenized to 15 foot or around 5 meters, and the average. The average is we take all the properties and then just average them, as usually is done. And you can see the fracture height is better preserved between the high resolution homogenized and less preserved between between high and average. And some fractures are better, some fractures are worse, but the overall, because we, again, in homogenization, we implicitly account for high resolution properties, we much better and preserve the fracture height containment much better for high resolution data using homogenization. Okay. But again, it's not enough to compare it for one fraction. Say, yep, this is a validation. It's better to do this in a more massive simulations, if possible. So, yep. So that's about it. Let me summarize. So I just said early on at the very beginning of the talk that we have this workflow or the method to simulate path scale developments, and we do upscaling of rock properties, upscaling of number of fractures, upscaling of simulator using ultra-fast simulator and the reservoir model. And here I just preserved just the first part, homogenization, again, which actually worked on in early 2017. And so the bottom line is that it's not a good idea to ignore high resolution rock properties, right? So when you average it for hydraulic fractures, so what we'll lose is change in fracture toughness in vertical direction, because this thin layering causes fracture height containment, and so the effect is about 100%. Okay, and then of course the correction for this vertical toughness in direction upwards and downward growth are different, so it's also very important. And another thing, which again I don't want to open this kind of worms, but this gives you the results demonstrate that when you homogenize stress, this is size dependent, right? So it says that your effective fracture toughness is essentially size dependent, and it scales as a square root of the layer size, right? And this is something that has been observed in lab experiments and the field data for magma dikes. So there is a lot of discussion in the literature of whether the fracture toughness should scale with fracture size, and in some models assume actually square root growth of fracture toughness with fracture size. And if you think about if you homogenize, right, to scale commensurate with fracture size, I mean, you'll get this square root of behavior of fracture toughness. So this is just an observation that this stress heterogeneities can be one of the reasons for apparent for these observations. Right? And acknowledgements. So the last slide. So thank you all for listening for this talk. So I'd like to thank the organizing committee and gang for organizing the series, and the labs for supporting me and my initiatives for the last several years. I'd like to especially acknowledge Roberto Saras Rivera for bringing challenging problems, right? So it's many things that I presented and mentioned. They originated from this phrase. When Roberto comes to my office and says, "Egor, we have a problem for you to solve," and so he always brings very interesting and challenging problems, which are very influential. Okay, I'd like to acknowledge Andrew Bunger for the discussions we had at the early time regarding homogenization and other things in early 2017. Bradley Abel, again, regarding useful discussion, some implementation of this. June, he worked with us. He did initial simulation again back in 2017 in Fracoptima. And finally, I'd like to acknowledge the Lawrence Livermore group, right, for their study, because because the homogenization has been kind of trade secret for a while, and with their with their paper and publication in this area, so we finally decided to give it a go and present and publish this work. So thank you all. So I'll be glad to answer all your questions.
Yeah, Igor, thanks. This is a fantastic talk, and glad to see the details actually behind all the button clicks, commercial softwares. Feel free to address the question for the folks. You type your question in the chat window. I see quite a few already.
Yes.
And go ahead. We have until 11.
Okay, let's start from the top right. So from repo, is the homogenization of Young's modulus only possible for periodic variation in Young's modulus? No, right? So we do these periodic cases as a validation, right? Because when you do periodic, when you homogenize, everything is homogeneous, and so it's easy to contrast, because if everything's homogeneous, if you just take the average for periodic cases, then you have just radial solution, right? And now you can see when you homogenize how different you are from the radial solution. But of course, we do apply it for field data on almost every project we do. K1C, H, and V are the horizontal and vertical toughness for the same layer. Yes. So K1C, H, K1C, V. So we assume that every layer has, and no matter what resolution you have, every layer has toughness, vertical, horizontal, elastic properties, leak off, right? Very often we can input the same high resolution horizontal and vertical toughness, okay? But once you homogenize, they become different, okay? So that's why right from the beginning, I kind of separated both of them. The next question, what fracture propagation criterion was used for these simulations? Here we use linear elastic fracture mechanics, right? So basically we say that stress intensity factor is equal to fracture toughness at the fracture peak, right? So there's no plastic zone here. And it is used in all simulators, as in ultrafast, in FracOptima as well. In the homogenization of stress, isn't the difference in upward and downward simply because of high in situ stress downward due to gravity? No, not necessarily, because when we homogenize, right, so we do have a trend, right? So if you go with this one, in this picture, the stress, right, we do have a trend of stress due to gravity, right? So stress increase versus depth, right? But this trend is captured well by the homogeneous stress, right? So here we always zoom near, say, several elements, say this one, and consider the differences just near the fracture tip. So this can be, of course, contribution of gravity, but I don't think it's the primary factor for it. Okay, so while all the modeling efforts are towards ability to model more complex in situ condition, what is the real value of this homogenization to better fraction operation? Well, that's a very interesting practical question. Again, see, this is part of the, I mean, first of all, we need to understand, right? I mean, homogenization tells us that the effect of all these thin layers can be very important, right? And what we see so far is that it leads to fracture height containment, right? And so if you ever need to do fracture modeling, right, and you do have to come up with a model, then you need to have, a sense whether the fracture say grows, to this layer or doesn't, right? And with using homogenization, right, essentially you have a better representation, right, of what could be happening, right? But I agree that the overall problems are very complex, right? We don't know many things, but we need to just gradually address them and see what's the effect of them is. Okay. Next question. In the case of the max, the layered solution should depend strongly on where exactly this layer with max toughness occurs. Okay, so yes, so it very much depends where how you select your mesh, right? And again, we did a lot of internal studies, I didn't show you, but some of them. So we tried to run it homogenization at different resolution. Say if you homogenize to 5 feet, 10 feet, 15 feet, and whether you move mesh a little bit, again, you do lose some things, but overall, I think it captures the results quite accurately. If heterogeneity of several variables takes place simultaneously, would you expect further demonstrations are needed? Possible coupling among heterogeneous. Yes, I mean this is again this is a good question. So ideally, we need to do several quantities at the same time for validation, and it's we did it partially. I mean, I didn't I don't want to show some incomplete results, but again, the procedures that we did, right? So it was based on some theoretical considerations, right? And so we use this example just for validation. So not just to try to kind of train the model and then apply it. So I mean, if we do believe in this theoretical consideration that it's not necessarily to do excessive computations, but it would be nice. It would be nice to do it. I think it's a very valid point. Can you comment on homogenization effect on proton transport? Okay, petal pattern shows extreme pinching near the wellbore, quite difference near wellbore risk profile to homogeneous fracs. Toughness should also increase as confining stress increases. Yes, so first of all, toughness does increase as confining stress increases because you essentially increase your magnitude of your stress oscillation. Regarding proton transport, this is not for homogenization of Fock properties, but doing the equivalent fracturing. And for this equivalent fracturing, again, in regard to proton transport, so we have these publications here. So we have one publication in review, and we hopefully, I mean, well, ARMA paper, right, is going to be published, right? So we have ARMA paper on this as well, in particular, on how to do this in the context of reservoir modeling. Okay, so that's, I encourage you to read these papers. Okay, so thanks, Anthony. And then next one, in your formula, the homogenization of K1C was based on periodic change of Young's modulus and stress. How to extend it for field data which is complex and not periodically varied? Is there any experimental work to validate the model assumptions? Okay, so, and well, again, so you see what I showed everywhere is theoretical formulas, right? So that something that can be applied to field data, okay? And the periodic cases were just given for validation. So in general, if you have layered properties of toughness in Young's modulus as shown here, I mean, you can apply this for non-periodic, right? But your answer, you cannot have, basically you need to compute it numerically, okay? Which is very quick to compute, but you need to do it for any set of field data. And we do it. And as I showed here for this example, we did it for the field data and just apply these formulas, all of them applicable. And regarding experimental work, that's again, we try to use the classical theories of periodic fracturing, right? So all these models are based on classical elasticity equation, lubrication equation, fracture toughness, linear elastic fracture mechanics, and so on. And these models have been validated, in different ways by different authors. So I think there is some indirect validation, but it also would be nice to do direct experimental validation of this work as well. Again, question about lab validation, right? Again, it would be nice. And then let's see, any more questions? Any questions? Okay, any comments on how to estimate K1C from E? Is it still valid, or does the ratio need to scale dependent? Yeah, I'm afraid this question is not for me, but for people who do petrophysics, right? So I'm not sure I can answer this one. Okay, right. And regarding email, so just contact Gang Khan, so he has my email. So how are you calculating horizontal stress in your simulations? What boundary conditions are you using? Okay, so for horizontal stress, again, this applies to any horizontal stress model. Okay, so I mean, if you want to introduce creep or any problem in stuff like this, it is possible. I mean, so far we use the simplest model. Okay, just essentially layer cake, elastic anisotropic for elastic properties, and we do apply tectonic strain boundaries, right? So they also affect minimum and maximum directions. So they also change the stress. Okay, so I think we are all done.